Let us now start discussing the Pareto optimality notion in quasi-linear domain. Pareto optimality or Pareto efficiency, as we have already referred to earlier, is a notion where we talk about the development of each of the utilities of every player, rather than maximizing the sum of or an aggregate measure of something. And also the difference is that in this Pareto optimality we'll have to look at the payment component as well, while in allocative efficiency we were just looking at the allocation component of the decision problem. So let us look at the definition first, and then we'll connect the Pareto optimality with the allocative efficiency. So what does this say? So we are going to call a mechanism in the quasi-linear domain to be Pareto optimal if for every type profile the following thing happens: that there does not exist any allocation, so a different allocation which is not equal to the allocation of f theta, and a set of payments pi 1 to pi n, with the additional condition that this payment is at least as much as the payment of the original mechanism. So if the mechanism is extracting this much amount of payment, allocation and the payment that we are going to talk about also at least extracts the same amount of payment, then this the utility under that allocation and that payment is at least as much as the utility when you are under this mechanism f comma p. So if there does not exist any such b and pi, then we are going to call that this is Pareto optimal. In some sense, you cannot really make it better for weakly better for all the players, and you can make it strictly better for one player. So of course this inequality is weak for all the players, and this inequality is going to be strict for at least one agent. So why do we need this additional constraint? Let us look at this. So if we so suppose we did not have this constraint, then what would have happened? One could have easily found some allocation and could have given sufficient subsidies. So maybe all these pi i's were negative, so that is the mechanism designer is essentially paying a lot of money to the agents, and therefore this inequality would have been very easy to satisfy. So we don't want that kind of a thing. So we also, in addition to the fact that this inequality should be satisfied, we also want that this counter example of this allocation and payment should be such that this payment at least extracts the same amount of money as the original mechanism. Alright, so now we are going to connect this notion of Pareto optimality. Simply speaking, the Pareto optimality is saying that if you are given a specific allocation and a payment rule, then there does not exist any other allocation and payments, the sum of the payments being at least as much as the sum of the payments in the original mechanism, such that all the players are better off in that new allocation and payment, and there is at least one agent who is strictly better off. So here we are going to compare the Pareto optimality with allocative efficiency. We are going to say that if it is Pareto optimal, then it implies, and it is implied by the fact that it is allocatively efficient. So this is kind of equivalent. So in this quasi-linear domain, we are not really looking at the payments. There is a reason for that. I mean, Pareto optimality and allocative efficiency are one and the same. So you don't really gain something more by defining Pareto optimality by putting restrictions on the payment. Rather, it is sufficient to look at the allocation alone. So let us try to prove this. We'll first prove in the forward direction, that is Pareto optimality implies allocative efficiency. Rather, we will prove it in the following way, that if it is not allocative efficiency, so that Pareto optimality implies allocative efficiency is equivalent to saying that if it is not allocatively efficient, then it is not Pareto optimal as well. So what does not allocative efficiency mean? That there exists some allocation which is not the allocation given by this mechanism, such that the sum of the valuation is at least as much as the sum of the valuation under that allocation rule f. So remember, what was allocative efficiency? It was looking at the sum of all these valuations a comma theta I, and summing over all the agents and picking that alternative which maximizes the sum, right? So this was allocative efficiency. So it is not allocatively efficient means that there exists some b which actually is larger than this sum, and this is going to happen for some theta. Now because this is larger than that, if we just look at the difference between them and define that as delta, that is definitely going to be positive by the choice that we have made. Now we are going to construct what do we have to show? We will have to show a Pareto optimality, a violation of Pareto optimality. So we'll have to create a counterexample. We already have found some allocation which could be a candidate allocation to form that counterexample. All that is remaining is to find the payment, and this is how we are going to construct that payment. So let's say this pi I. So here it is sum over all the agents. We are looking at the individual differences. So VIB theta I minus VI of F theta theta I, and then we are summing the payment. So this payment is originally given because that is the mechanism itself. So we are given the mechanism. We are just using the same payment here and subtracting out this delta, so which is guaranteed to be positive, by n. Now why we have chosen this specific form will become clear in one or two steps. So now what we can say is because we have our candidate, and this we are going to define for every I in n. Now this candidate payment and the allocation B is our counterexample to Pareto optimality. Then we should be able to show that the utility here, which is VIB of theta I minus pi I. So just look at the corresponding example. So this definition of Pareto optimality. If this happens, then we are certain that this is not going to be Pareto optimal. So we write this left hand side minus the right hand side here. So minus this right hand side, and we see that that is equal to delta over n. I mean, this is just reorganizing this equality here, and because of the fact that this delta is positive, strictly positive, then this inequality will be positive. That means that for every agent I in this new allocation and payment, the difference between the utility of that player is getting strictly better off than the allocation and payment under the original mechanism. And we are also not violating the payment condition because if we just take the sum over all these pi i's, you can see that this sum, this difference is exactly equal to delta if you are summing over all the agents. So once you sum over all these agents, all that you are and you are summing over this delta over n, so this will become exactly equal to delta, and that is exactly equal to this part. So these two parts will cancel out. What will be remaining is the sum over all this pi. So this pi I is exactly equal to sum over pi's. So we are also maintaining that payment condition. So we found that f is not Pareto optimal, and here is that counterexample. Okay, so we have proved the forward direction. Now let us look at the reverse direction, and we are going to prove it in a very similar way. Reverse direction means that if it is allocatively efficient, we'll have to show that it is Pareto optimal. Rather, we show that if it is not Pareto optimal, it cannot be allocatively efficient. So what does not Pareto optimal mean? That there exists some allocation and these payments such that this payment inequality, the payment constraint is met, and also this inequality holds for all agents in weak form, and then it is strict for some agent j in n. Now if you just sum over all these inequalities, because this inequality is going to be strict for some j, so this weak inequality will become strict inequality when we are taking the sum over all of them. So fair enough. Now we are just looking at the difference between this sum of these valuations under B and the sum of the valuations under F, right? So we are just transforming it on the right hand side. So we can see that this is strictly going to be larger than sum over pi I minus this sum over pi theta I. Because of the assumption, so because this is not Pareto efficient, so this inequality is also going to get satisfied. So we see that this particular term, the right hand side of this inequality, is actually non-negative, and that implies that this is this at B, the sum of the valuations of all the agents is getting strictly better than the sum of the valuation at f of theta, and therefore f of theta is not an allocatively efficient allocation. So that essentially proves both the directions. So as soon as we have Pareto efficiency or Pareto optimality in this quasi-linear domain, we can immediately say that it is allocatively efficient and vice versa. Now let us look at the allocative efficient rule. So now we don't really have to worry much about the Pareto optimality because both are the same. We can focus on allocative efficiency. Now what we can see is that this allocative efficient rule is actually implementable. So how do we design payments? So we have made this point earlier that whenever we say that a specific allocation rule is implementable, that means there exist some payments which will implement that in dominant strategies. So so this rule is the rule which maximizes the sum of the values of all the agents, and we will have to just construct the payments. And we are going to construct the payment in the following way. And this particular structure is named after Groves, who has actually given this structure. So what we are going to look at is first for this while designing the payment for player I, we are defining a function hi, which is not a function of theta I, the type of player I. It is dependent on the types of all the other agents. And the second term, and from that we are subtracting out the sum of the values of all the agents except agent I under the same outcome. So F efficient is essentially the allocatively efficient outcome, the allocation in this context, and we are just looking at that, but except agent I. Now this function hi could be arbitrary. So you can pick any number. It can be constant, it can be zero, whatever it is, but it gives you the complete flexibility. So what does that mean? Let us look at this kind of a payment rule using an example. So suppose we have single indivisible item allocation, and there are 4 agents here. Their types are given in the following way. The types are given by theta 1 equal to 10, theta 2 8, theta 3 is 6, and theta 4 is 4. When they get the object, so this type means that this is the value that they get when they get the object, 0 otherwise. And let us also fix this hi theta minus I to be the minimum of theta minus I. This is just an arbitrary thing. I mean, you could have chosen some other numbers. The corresponding payments should have been different. Now if everyone, so let us assume for now, we will later prove that this is also true, that if everybody reports their true type, then the values of this hi are going to be as follows, and you can verify that. Now the efficient allocation gives this item to agent 1. Why? Because if you give it to because this is single indivisible object, if you give it to this agent, you are maximizing the sum of the values, right? So that is why it is allocatively efficient. Now you can define the corresponding payments, and payments exactly as we have defined in this case. So this is going to be hi theta minus I minus the sum of the valuation of all the other agents when it is when the allocation is efficient. So in the efficient allocation, only agent 1 gets this object and nobody else gets this object. So therefore the valuations, the sum of the valuation of all the other agents is going to be 0, and that agent gets gets this hi. So this h1 is exactly equal to 4. So this is going to be the payment for player 1. Now when you are looking at player 2, you know that the sum of the valuation, so the efficient allocation gives it to the agent 1, so whose valuation is going to be 10. So that is the number that we are putting here, and this one is the H2, and we see that H2 is also 4. So this difference is -6, which means that player 2 is getting paid 6 amount of money. And similarly, you can carry out the rest of the calculation. You will see that only player 1 is paying and other players are getting paid. So that is an example how, if the players were reporting their types truthfully, what will happen in this context. Now we are going to make a stronger claim. We are going to claim that this mechanism, this Groves payment mechanism, essentially Groves is a class of mechanism because you can just change the HIs and you can get a bunch of payment rules, and all of them are essentially members of the Groves mechanisms class. So all this class of Groves mechanisms are DSIC. Now why is that? In order to prove DSIC, we will have to satisfy that inequality that we have already defined, and let us do it in step by step. So we are just focusing on player I, and we are arbitrarily picking this player I. So therefore, this is without loss of generality. Suppose its own true type is theta I, and other players are reporting theta minus I tilde. So if this agent reports its type truthfully, then the outcome becomes A, and if it misreports to some theta I prime, then the outcome becomes B, right? So by definition, we know that because this is allocatively efficient, this VI AI theta I plus this thing, so we are just writing the sum of the valuations of all the agents at A when this agent is reporting its type truthfully, and we are just decomposing it. There is a purpose why we are doing this decomposition, because this particular decomposition will show up later in our proof, and we'll use this inequality. And this is going to be at least as much as any other allocation. In particular, if you put B as well, this will also be larger than that, because A is essentially the allocatively efficient outcome. So whenever we are looking at this type, so this type is the true type theta I. When its true type is theta I and you are trying to maximize it, you will get the allocation A as your outcome. B might be an efficient allocation when you are looking at treating as if the player I's true type is theta I prime and not theta I. So when its true type is theta I, A maximizes this sum over all the other alternatives, in particular the alternative B as well. Okay, so let's save this equation 1 and we'll reuse it. Now what do we really need to show? So utility of player I when he reports theta I is at least as much as the utility when he reports theta I prime. So let us write down the left hand side of the DSIC inequality. So this is the left hand side. So we have the rule is nothing but F efficient. The mechanism is F efficient, and P1 up to Pn. This is the mechanism. And under this mechanism, what is the utility when player I is reporting his type truthfully? That is reporting its type to be theta I, and the other players are reporting their types to be theta minus I tilde. That is given by this. So player I is reporting theta I and others are reporting theta minus I tilde. Similarly, the payment is calculated according to that, and we are evaluating, player I is evaluating this utility when its true type is theta I. That is its true type, and therefore this inequality should hold when its type is theta I. So let us write this down. Writing down the payment function. So we already know that the payment is given by this Groves payment rule. So we can just expand that out by hi theta minus I tilde, and the other part is the sum of the valuation of all the agents except agent I at the same efficient allocation. So now there is a reason why we have chosen this structure of a specific form. So now we know that this is nothing but A, because that is the allocation when agent I is reporting its type to be theta I, others are reporting theta minus I tilde, and that is the same here as well. So we can club these two things together, this and that, and then we can write that this is going to be the sum of the valuations of all the agents, right? So sum of the valuation at the efficient allocation. And because of that fact that this is essentially maximizing the sum, so what is the definition of efficient? Just do this exercise yourself. So fi theta I and theta minus I tilde, what is it? It is actually the argmax over the summation of all these vi's a of theta I. So you can imagine that this you can just write. So instead of writing it in this way, it is better to write it in the following way. So we just isolate this theta agent I because its type is theta I. For all the other agents, so sum over vj's, where it is a and theta minus, so theta j, so this is agent j, theta j tildes, j is not equal to I. So if you look at this sum here, it is actually maximizing this sum, and because this is the f efficient thing, then we can actually write it this to be greater than equal to. So whenever we are plugging the same value inside this a, we are going to get this this sum to be greater than equal to the same sum vi of theta I plus the sum over all these things for every other b which is not equal to a, and that is exactly what we have written here. This is the inequality 1, and we are just now using the same fact that this is because this is greater than or equal to any other alternative. In particular, when we are looking at this alternative b, which is nothing but when player I is reporting its type to be theta I prime, and yeah, so that's it. We can actually write the same inequality here. This will get satisfied. Think about it. I mean, this will be clear because there is a little bit of notation involved. It might get a little confusing in the very beginning, but remember the fact that agent I's true type is theta I, and this is exactly where we are trying to maximize it. So everywhere you will look at that what is happening when we are trying to maximize this. We are looking at agent I's true type is theta I, and that is why it is the argmax on that profile of thetas, and therefore this is going to be greater than equal to this inequality for all b's which are not equal to a, and in particular this inequality will hold whenever we are speaking a very specific outcome, which is theta I, when agent I is reporting theta I prime and theta minus I, others are reporting theta minus I tilde, and we are running the same efficient allocation. This could be a different alternative, a different allocation, but for that allocation this inequality should hold, and that is essentially the end of the proof. Now we can club these two things together. So notice that this is completely independent of the type reported by player I, so this will not change, and this two things together we can write it as the payment of agent I when it is reporting its type to be theta I prime and others are reporting theta minus I tilde. So together you can write that this right hand side is nothing but when he is misreporting, when the agent I is misreporting to theta I prime, this is the utility that it gets. And because of this inequality is getting satisfied, we can say that this mechanism F efficient is implemented by this gross payment rule. So actually this gross mechanism, the class of gross mechanism, is actually dominant strategy incentive compatible. That is because of the fact that we have shown this for any arbitrary I, so you can repeat this argument for any I, and this inequality will hold for all I in a